Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. And I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource material. We also steer in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with the research agenda for the system operators. More information on the GPST can be found at globalpst.org. We just had a great in-person forecasting and markets workshop in Salt Lake City the week of June 10. Just as with our webinar today, we had participation from NOAA and Camus Energy, along with a broad cross-section of the industry. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform, so please ask your questions through Slido. Go to slido.com and enter ESIG24 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. So today's topic will be on the application of NOAA's Open Data Dissemination weather forecasts. Weather forecasting is a topic we've been talking about at ESIG for at least the last 17 years or more, as evidenced by the 17th annual Forecasting and Markets workshop I mentioned just a few minutes ago. And just this past January, we had Dave Turner, the manager of NOAA's Atmospheric Science for Renewable Energy program, present a webinar on the latest developments in the HRRR, or High Resolution Rapid Refresh model, before it is replaced by the Rapid Refresh Forecast System, the RRFS or the RUFUS. As you will hear in today's webinar, this is a topic where continuous advances are being made, with much of the work driven by feedback from users like yourselves. So I would encourage you to be in touch with the presenters if you have some ideas of future developments you would like to see. Today's webinar will be presented by Adrienne Simonson, Director of NOAA Open Data Dissemination, and David Stuebe, the team lead for forecasting at Camus Energy. Adrienne, in her role at NOAA, leads strategic efforts for open data and internal and external engagement across public, private, and academic enterprises. David has 2 decades of experience working with meteorological data and cloud computing, which he is now using to help build a state-of-the-art forecasting product for grid applications. Both NOAA and Camus Energy are regular participants at ESIG, and I feel very fortunate to have Adrienne and David here with us today. This webinar will discuss how NOAA's Open Data Dissemination program provides public access to weather forecast models that provide grid operators more accurate and precise weather prediction data for real-time operations. Utilities are actively using these weather forecasts to inform and improve real-time operations. The webinar will also provide an introduction to all the NOAA environmental data available to the public and highlight how utilities and technology providers can leverage these open source data sets. I greatly value the contributions of NOAA and Camus Energy to the industry, and I look forward to what they have to say. Just a short reminder once again to use Slido at slido.com, with the event code of ESIG24 to ask your questions. Okay, without any further ado, let's go ahead and get started. Adrienne, I will now turn it over to you.
Great. Good afternoon, or wherever it is, whatever it is, wherever you all are. It's a pleasure to be here with you all today. Thank you so much for the invitation and the introduction, Charlie. I'll note that I have most of the NOD team along with me to help answer questions, including our program manager, Patrick Cowan, our engagement lead, Jenny Disson, and our communications lead, Kate Zura. Next slide, please, Kate. For our agenda today, first we'll explore NOD's purpose and mission, then we'll review the available data and how to find it. Next, we'll discuss NOD's programmatic structure and operational support for users, including how and why we communicate with them, and as well as our goals to help understand their needs and help them utilize the resources. Then I'll close out with a couple of case studies before handing the mic over to David Stuebe for his portion of today's webinar. Next slide, please, Kate. Now let's talk about NOD. NOD began as a research project in 2015 in response to the exponential growth of NOAA data. NOAA wanted to improve users' experience as well by making the data easier to find and access. Today, NOAA Open Data Dissemination, or NOD, provides open data from each NOAA line office via 3 cloud service providers, or CSPs, Microsoft Azure, Amazon Web Services, and Google Cloud. By harnessing the scalability of the cloud, NOD provides end users with improved access for NOAA data and reduces their reliance on internal NOAA systems. There are no use restrictions. User registration is not required. Appropriate metadata is provided. Most significantly, there are no egress or data download costs for the users or for the agency. This is because NOD leverages the CSP's expertise, platforms, and tools via unique public-private partnerships that democratize NOAA data dissemination and allow for interoperability and innovation to solve societal challenges. Next slide, please, Kate. The Foundations for Evidence-Based Policymaking Act, including Open Data Act requirements, commonly referred to as the Evidence Act, was signed into law in January 2019. The Evidence Act requires open or unrestricted governmental data to be freely available to the public. The development of NOD since 2015 has been both effective and timely because of its ability to support NOAA programs in adhering to Evidence Act requirements by, number one, making NOAA data assets publicly available via our 3 cloud service provider partners, 2, publishing data assets as machine-readable data, 3, maintaining a data inventory on our webpage, NOAA.gov/NOD, with easy links to the cloud service provider landing pages. 4, engaging the public in using the data assets of the agency in order to expand use of those assets, like today's webinar and NOD office hours, which we'll discuss later in this presentation. And finally, 5, providing the public with the opportunity to request specific data assets directly or through their CSP. NOD's user engagement and customer experience efforts are designed to encourage use of NOAA data, collaboration among partners, and incorporation of feedback from users. That's how NOD supports users of the data, as well as how it supports the NOAA Chief Data Officer and NOAA line offices, programs, and data owners in meeting their Evidence Act requirements, as well as the administration's priorities listed on the right. Next slide, please. There are hundreds of NOAA datasets accessible via NOD from across NOAA. I'll let you read the full list, but I want to highlight that it includes near real-time datasets that can support public user operations, including geostationary and low Earth orbit satellite data and products, plus a variety of weather models and forecasts from across NOAA. NOD often builds a full period of record for select data holdings based on CSP and data provider requests. NOD datasets are machine readable, and NOD is included as a data provider partner in the National Artificial Intelligence Research Resource Pilot announced January 24th. I'll note that only a few NOAA datasets are AI ready to date, but they are available on NOD and more AI datasets are in progress. A full list of NOAA data available is listed on the NOD website, NOAA.gov/NOD, which includes direct links to the dataset landing pages on each of the CSPs. There's more than 59 petabytes of data on NOD as of today, late June, Q3, fiscal 2024. Next slide, please, Kate. On this slide, we've highlighted NOAA data sets of interest for the energy sector available on NOD. Much of these data sets, but not all, are near real time. There are a variety of numerical weather prediction models listed and weather and climate data, as well as next-generation weather radar. In addition, data from 2 specific satellites of interest, NOAA's geostationary operational environmental satellites, including data from 16, 17, and 18, are available on AWS and Google Cloud with a subset of products on Microsoft Azure. There's also a curated set of GOES 8 through 15 in area format. These are which is not the official format used for those missions, but those are available on AWS and Google Cloud. I'll note that end-to-end transfer latency tends to be about 24 seconds for GOES 16 products. NOAA's Joint Polar Satellite System, including the SWOMI National Polar Orbiting Partnership and NOAA 20 and 21, are available on AWS and Google as well. While these are not complete periods of record, that effort is ongoing, with an eventual full period of record available on Google Cloud and possibly AWS. Until then, some have been backfilled and some data has been reprocessed, but not all. I'll note that the latency is similar to GOES-R. Next slide. NOD facilitates end users access and use of high-volume NOAA satellite data via the cloud, allowing for scalability, ensuring sustainable, stable access by users, especially those needing near real-time data, and supporting a high volume of users as well. Next slide, please, Kate. To give you an idea of how this works from an architectural perspective, the NOD pipelines begin with the data that originates in each of NOAA's line offices and resides on NOAA's on-premise systems. For those who may be unaware, there are 6 NOAA line offices, of which the National Weather Service is just one. The data is either pushed by the NOAA line office or pulled by the NOD data broker to any or all of the 3 cloud service providers. Users like yourselves can access the data through the links on our website to the public data programs of each of the CSPs or through their public dataset programs directly. Data alerts and updates via SNS, PubSub, and Azure event notifications may be available. Please refer to the CSP landing page to see if a dataset of interest has an event-driven notification set up. Next slide, please. NOD is scalable by design and is not constrained by costs, since egress is free and there are no annual contract costs for NOAA. As a result, NOD is orders of magnitude more resilient than on-premise systems. The graph on the slide highlights that NOD holdings on AWS have supported sustained interactions by count of 1.2 to 1.5 billion per day for 28 days straight for GOES-R data. NOD has seen interactions by volume of 1.2 petabytes of data in a single day with no impact to other users and absolutely no egress costs for the users or for the agency. This is not possible or cost-effective with on-premise systems. Next slide, please, Kate. The NOD team released a publication in September titled NOAA Open Data Dissemination, Petabyte Scale Earth System Data in the Cloud in Science Advances. This article dives into detailed usage metrics on one of our 3 cloud service providers, AWS, revealing wide use of NOAA data on the platform and highlighting the value of hosting NOAA's data on the cloud. NOD holdings on AWS see sustained access of more than 5 petabytes of data per month and more than 1 billion interactions per week, with occasional sustained interactions of 1.5 billion per day. NOD hosts a number of key data sets on the public cloud that are both heavily used and frequently updated, like numerical weather prediction models or satellite data. The Science Advances article delved into the fact that for certain data sets like those I just mentioned, access is far greater than uploads. For example, on AWS alone, for every byte of GOES data uploaded, it is accessed or touched 25 times. For Himawari data, that increases to 34 times. Himawari data is another geostationary satellite we have. It's the Japan Meteorological Satellite. In addition, as you can see via the bar chart, the percentage of accessions originating from AWS-owned IP addresses is trending upward over time. Heavy use of NOD holdings on AWS, 10 to 20 times greater than baseline, is driven by on-cloud resources. This strongly suggests that the bulk of users are availing themselves of the tools provided by the CSP platforms rather than egressing the data, especially for large analyses not typically possible by traditional infrastructure. Next slide, please. Kate. But NOD is more than a technology or a contract. NOD is an ecosystem. This is because data really only have economic value when they're used in decision-making. And now that the data is in the cloud, cloud users look to NOAA for data, information, and tools in order to use that data in decision making. But reliance on cloud is still relatively new, so their needs vary across the board, across sectors, and across levels of experience. NOD provides timely and informative responses to all these user questions, as well as technical and scientific support, and loops in internal data owners and stakeholders, including CSPs, where appropriate. Users can opt for service delivery notifications of the datasets, as previously noted. The CSPs are also interested in understanding their user community's needs and collaborate with NOD to provide technical as well as communication and engagement tools to reach users, inform them that data is available, and answer their questions. In the graph on the right, the NOAA logo represents the LOs and their data. NOD, the cloud service providers, other partners, and public users work with NOAA to ensure that the data is accessible and performant. NOD is continuously looking for ways to connect with our users in order to understand their experience and improve it. Engagement is key to understanding their use cases, so NOD's targeted engagement activities focus on prompting users to reach out, including webinars like today's, or participation at flagship conferences like our American Meteorological Society, and a relatively new concept called office hours that we'll explore in a minute. First, let's talk about who is using NOD. Next slide, please, Kate. NOD does not require users to register or be authenticated to access the data on the cloud. So we only know who the end users are if they tell us, and that's usually because they have a question. NOD is the delivery vehicle, if you will, for NOAA line office data. So our most important users are internal. Some of those internal scientists and staff find unique ways to utilize the simplicity of accessing authoritative NOAA data via NOD for their own programs, as do a variety of federal agencies. I'll also note that all of our CSPs have internal teams that utilize the data on NOD, such as Google GraphCast or Aurora, which is Microsoft's AI that is a foundation model of the atmosphere and is reportedly first to predict air pollution in the entire world. But end users come from a variety of sectors and data experience levels. The sectors range from public and private multinational to small end industry users to intermediary software product or services solution providers. This includes, in the past year, fintech, energy generation, delivery and trading, and climate tech and innovation as a few examples, because the list is just too long to verbalize. NOD routinely responds to emails from highly skilled cloud analysts who reach out with nuanced data access questions, or from users who are just beginning to work with either the data itself or the cloud as a new access option. Next slide, please, Kate. But if we don't know who the users are, how do we support their use of NOAA data? How do we help users and potential users to learn more about using NOAA data in the cloud? NOD needed a targeted way to understand users' experiences so we could continue to improve them. NOD engagement lead Jenny Disson developed the office hours concept in order to connect with users and give them an opportunity to ask questions and listen while other users ask their questions of the dataset subject matter expert, the CSP, or NOD in a relaxed environment. Each virtual session is an hour and 15 minutes long, focused on a specific data set, and co-hosted with the relevant NOAA line office and one of our 3 cloud service provider partners. Our 2 most recent office hours, both of them on joint polar satellite system products, were held on April 18th with Google Cloud and June 13th with AWS. Visit our website at noaa.gov/NOD to view materials from past office hours, including slide deck presentations, user questions, and subject matter expert answers, and other resources, including recordings. The materials from April 18th have been posted, and the June 13th session should be posted in the next week or so. You can also view upcoming office hours and register for them from noaa.gov/NOD. Registration is required for office hours for invitational purposes only. The data itself continues to be accessible without registration. Whenever you have a question, email us at nod@noaa.gov. That's nod@noaa.gov. Next slide, please, Kate. NOD works with users to develop use case studies to show how specific environmental data can be applied in real-world scenarios, making it easier for others to understand its potential and practical uses. Case studies serve to encourage wider adoption of environmental data practices and technologies. And case studies allow NOAA to understand the application of its data in a specific and targeted context, showing the linkages and connections between our data and its role in decisions that improve societal outcomes. With that in mind, let's explore a couple of case studies. First up, already on the screen, is Enverus. Enverus is a leading energy-focused software as a service platform that provides data analytics and insights for the oil, gas, and renewable energy sectors to help companies optimize their operations and strategic decision-making. They recently acquired Circle Solutions, which is a former NOD case study, and developed AI-based energy forecasting solutions, specifically wind and solar forecasts down to the turbine and farm level to those participating in wholesale markets. These analytics help balance the supply and demand side of energy. Their AI method uses the High Resolution Rapid Refresh model, or HRR, for both near real-time and historical data. Enverus pulls the near real-time data through NOAA's NOMADS environment and accesses historical HRR data via NOD using AWS. All data and conversions are completed within their own cloud environment. NOAA is one of Enverus's most important partners for providing information to the energy industry. Next slide, please, Kate. And this is one more critical case study, and my last slide for today. Camus Energy is a software as a service company that provides grid management software to distribution utilities. Camus delivers distributed energy resource orchestration in support of zero carbon grid operations. Camus uses high-resolution rapid refresh, or HRR, data via Google Cloud in machine learning models that forecast load and generation for the distribution system from minutes to 48 hours into the future. As part of this case study, Camus shared the impacts and benefits provided for distribution operations via improved forecasts, but I'll let our next speaker, David Stuebe, get into the details for you, because David Stuebe, the forecast team lead for Camus Energy, is the instigator of today's webinar and is up on deck next. With 2 decades of experience helping with meteorological data and cloud computing, David has helped Camus Energy build an industry-leading grid forecasting product. We value his input and look forward to hearing his thoughts today. We also value this industry and your input and feedback to NOAA's Open Data team. We look forward to your questions and comments. Over to you, David.
Thank you so much, Adrienne. Instigator is a good word for me, I think. Let's see if I can share screen. Right. You have me now. So thank you so much, Charlie, for the invitation to speak, and thank you, Adrienne, for that wonderful introduction. I'm so excited to be co-presenting with you here today. The collaboration between Camus Energy and NOAA Open Data Dissemination, along with all the people and organizations that support the technology behind the data, really ties together 20 years of my career. I started out as a seagoing observational oceanographer, fascinated with how the ocean moves and mixes. And after 4 years in the MIT Hui Joint Program, I went to work at UMass Dartmouth, building my first forecast system for the waters of the Gulf of Maine. And I immediately found myself neck deep in data systems, file formats, and metadata standards. Oh, next slide, there we go. 20 years on, I'm now a machine learning data engineer, which really isn't so far from my roots, since both oceanography and data engineering mostly boil down to glorified plumbing. My big tech coworkers laugh when I tell them my first programming language was Fortran, but the story I'm here to share with you could only happen by crossing over between many communities. So now I'm the forecasting team lead at Camus Energy. We build software systems for distribution grid operators to understand where and how to use distributed energy resources to deliver safe, reliable, and affordable power. Our team leverages decades of experience designing, operating distributed systems for companies like Google, Uber, and SpaceX. Our team brings together the knowledge gained from building and scaling some of the world's most complex systems with hands-on experience serving utilities through organizations like NREL, GE, and NLX. To this mix, I added my experience working in environmental science data with NOAA and IUs during my time at UMass Dartmouth, and consulting for RPS and leading the data management team for the Ocean Observatories Initiative. Camus' grid orchestration platform brings together siloed data systems and business functions at distribution utilities to unlock value from the dynamic management of distribution grid resources. For the first time in 30 years, the distribution system is growing rapidly with new industrial and residential loads. Load growth combined with new distribution-connected generation and storage is transforming the role of grid operators. They're no longer just planning service upgrades and responding to outages, but orchestrating distributed energy resources. The Camus platform allows grid operators to dynamically maximize the value of the distribution grid, and the key to that capability is awareness of what's happening now and foresight into what's happening next. We'll come back to the value of forecasting to the distribution grid at the end of the presentation, but for now it's enough to know that we need to forecast the load at every point in the distribution grid. Now we're going to dive deep into how Camus is contributing to a thriving open source community that enables access to environmental science data and NOAA's forecasts in particular to power our grid forecasts. Previous ESIG webinars on weather data went into great detail, framing the difficulties of using numerical weather prediction data and exploring how operational numerical weather prediction works at NOAA. Justin Sharp's Mind the Gaps presentation in the ESIG report, Weather Data Needs for Planning and Analyzing Modern Power Systems, provides a great framework for what we're talking about today. Where Justin was focused on long-term planning, this presentation is primarily focused on operational forecasting, and where he described many of the difficulties across a range of requirements shown here, we're primarily concerned with the usability requirements in green on the right: data curation, public availability and accessibility, and transparent documentation. While my work at Camus so far is focused on operational forecasting, the technical solutions for availability are certainly extensible to planning, especially where historical reanalysis data is available via NODD in the cloud. Dave Turner's presentation on NOAA's Rapid Refresh system provides a great overview of how numerical weather prediction works. I'll further simplify here, just saying enough to understand the structure of the data we get from the weather forecasts. The forecast system runs several times per day. Each run is one cycle. During each forecast cycle, the latest observational data from radar, satellites, and ground stations is assimilated onto a mesh that represents the properties of the atmosphere in billions of small cells. The water, wind, and heat of the simulated atmosphere are then moved and mixed between the cells by a supercomputer, integrating the equations of fluid motion over time. All the stuff happening in the atmosphere that's smaller than the mesh must be approximated by the physics suite. For this to work, we have to simulate the whole atmosphere, the whole world, all the time. We do this at coarse resolution with large cells, making longer predictions up to weeks in the future. The global model results become the boundary condition at the edges of more detailed model covering North America with smaller cells. For electrical engineers, this should feel familiar. We're solving a boundary value problem with an initial condition. The resulting data set is large and complicated, especially when you want as much historical data as you can get to train a machine learning algorithm. Numerical weather prediction systems produce huge volumes of data, including all sorts of meteorological variables. For instance, there are 6 temperature variables that you might consider if you wanted to know how hot it's going to be for a load forecast. To get the temperature at a particular location, you need to use the geographic projection to get the value from the right cell in the mesh. All this data is packaged up in big binary files using standard file format called GRIB, originally designed for tape drives in the 1980s. Each forecast cycle produces a new GRIB file containing a new, more accurate temperature forecast, which can be used to update a meter load forecast. The grid load forecasts work differently than the physics-based weather forecasts. The load at a meter is controlled by human behaviors with plugs and switches, not laws of physics. The grid forecast is a regression model that learns what the load is likely to be based on historical correlations. This is called supervised machine learning. I won't go into the details of how we build our machine learning models in this presentation, but for now I'll just say that it's not generative AI or ChatGPT. For today, we're focused on how we manage the weather data, a critical input to the regression model. For our operational forecasting needs, Camus has focused on just a few of the many available forecast products from NODD, specifically the high-resolution rapid refresh and the global forecast system. We've pulled together this overview of the key properties for internal use, but I hope that it might be useful for others, a step towards curation that supports usability. Going through the HRR surface products, a full 48-hour forecast is run every 6 hours, but an 18-hour forecast run is run every hour, producing the staggered pattern you see in the forecast model run collection diagram on the right. The x-axis is the forecast run time, what time the forecast started, and the y-axis is the forecast valid time when the forecast is, well, 4. The HRR model produces one grid file per forecast hour covering the lower 48 states as shown in the map on the left. As I said, this produces a lot of bits and bytes, 10 to 30 terabytes per year, and hundreds of thousands of grid files per model product from HRR. The GFS and global ensemble forecast systems produce an order of magnitude more data, and this is only the surface data, not the full 3D mesh of the model. How do you manage this much data efficiently for machine learning? Until recently, best practice for using forecast archives was to download millions of files, terabytes of data. Storing and serving all that data locally is expensive. Extracting specific regions and reordering the bytes as a time series for particular points can help for historical studies, but is much more difficult to build and maintain operationally. Cloud storage changed everything. Cloud storage, as in AWS S3, Google GCS, and Azure Cloud Storage, are the big three. They're perfect for storing huge archives of forecast output. It is much more scalable and reliable than an FTP server and a perfect solution for NODD to share weather data with the world. Because cloud storage is so scalable and fast, we don't need to download years of forecasts locally. There are a lot of problems with grid files used for weather forecasts, but the crucial feature that enables machine learning in the cloud is that you can read just the bytes you need for a particular time and a particular variable from the grid file. Doing this via cloud storage, requesting thousands of variables per second, is what makes this approach to machine learning scalable. And crucially, NODD's partnership with the cloud providers covers the cost, as Adrienne said. A whole ecosystem of open source tools is developed around using cloud storage to store big arrays of scientific data like weather forecasts in lots of small blobs. The key discovery was that most legacy file formats support this byte range access, allowing these new tools to view collections of old files moved to cloud storage as a single huge data set without having to copy or transform the data. You just need a map of where the bytes are. Unfortunately, building the map for grid files in particular is extremely slow and expensive. You have to read all the grid files. Camus has contributed new methods over the last year to make this process even better. First, rather than reading terabytes of grid files directly, we can read the small text header IDX files that NODD publishes alongside the grid data to build the map of byte ranges. Second, rather than building a singular dataset mapping file for every new forecast, we can store the index data in a database. The index can then be queried by our machine learning models and combined with static metadata about the weather forecast to generate a specific data set of variables for a specific time range needed for the forecast. Then we read just the bytes we need for each variable from the NODD cloud storage archive of grid files. And again, the key point is that we don't pay to read the data. NODD's partnership with the cloud providers covers the cost. So why did Camus Energy, a small tech startup, invest our time and energy in this? Let's get to the specific improvements. These improvements created this incredible leap in our ability to integrate weather data into our grid forecasts at scale. There are 5 major concepts we implemented and have now shared for others to improve on. I go into some detail about these changes in the Pangeo Discourse webinar linked below with the source code available. We have shared this in the hopes that others will make it better. With this work, we're building on an existing open source community that has a great track record of producing reliable Python data science tools. The impact of these improvements on our operations is tremendous. We can now build indexes of NODD grid archives with little to no effort and minimal cost. It's hundreds of times faster and more flexible than what we were doing this time last year. Once we've built the index, we have all the weather data forecast products and variables at our disposal. And with the improvements to the ZAR library, we can now train models over 4 years of data. That's 35,000 hourly time steps, each one read from NODD cloud storage at request time. During model training, we get the most value out of the parallelization with sustained read rates between 1 and 2 gigabytes per second across multiple workers training many models. This snapshot from our monitoring system shows 4 workers training our meter level models over 4 years of data. It shows total CPU use in the top panel and the IO rate in the lower panel. There's still room for improvement here, but this kind of sustained utilization from a Python process is a big deal. The overhead of the parallelization reduces the efficiency when running the predict method that only requires a few hours of data, forecast data, but we still see significant improvement and much higher sustained CPU utilization that gets us down to the 2 cents per meter year forecast value. We did not do this alone. We built on a thriving ecosystem of Python data science tools and organizations. The benefits of this approach are enormous, and we've contributed our source code back to the community to help foster more collaboration. By adopting and contributing to community tools, we also get a full suite of web services to visualize and explore the weather forecast data. This is a key part of improving accessibility. Seeing is believing. The work I've described here builds on an existing set of tools to optimize inefficiencies and improve operational cost. At the base of the stack are the cloud service providers and their cloud storage partnership with NODD. NODD, as Adrienne described, is the operational NOAA data dissemination program that makes data available to the public via highly scalable cloud providers. This valuable public resource is available at no cost to the user via the cloud storage API and has vast potential applications in research and industry. That potential value is driving many individuals and organizations to contribute to the open source tools that maximize the leverage on this public data set. The most critical link, and the part that we've contributed to through this work presented today, is ZAR and Kerchunk. I don't have time to give all the credit that's due to the many folks that have contributed, but I do want to raise awareness of the individuals and organizations that have directly contributed to Camus' work in the last year. I first want to thank RPS and IUs for inviting me to participate in the Reach for the Clouds project and allowing me to share much of the source code for the work I presented today through their GitHub project. The Earth System Information Partners, ESIP, not ESIG, has also facilitated much of the collaboration through their Slack chat and other community efforts. Pangeo is providing a platform for discussion and collaboration with the developers of ZAR, Kerchunk, and Xarray. NumFocus and PyData provide organizational structure and stability to much of the open source ecosystem. Open Climate Fix is a nonprofit organization working with National Grid to use computers to reduce carbon emissions. And they've identified the same accessibility challenge for weather data as the major obstacle to their technical solutions using machine learning. ECMWF builds and maintains the Python library for reading Grib, and finally Anaconda and their support for Martin Durant, who's been an instrumental collaborator in our work and lead author on FSPEC and Kerchunk, which pioneered the core capability to build aggregations of Grib files from cloud storage. Martin is in fact working with a Google Summer of Code intern to move some of the work I've described here from the open source IU's DMAG GitHub repository into a more usable form as part of the Kerchunk library. Okay. Thank you for following me down the rabbit hole of the technical details of using NODD weather data for machine learning. If you followed me this far, please stay with me for 3 more slides while I pop back up a few levels to explain the essential role of forecasting for the distribution system operator. There are 2 primary use cases that provide value to utilities and their customers as distributed energy resources enter the distribution system. Peak demand reduction is a direct financial incentive to flatten peak load by deferring demand or releasing stored energy. The exact form of the financial incentive depends on the utility, their energy supplier, and their regulatory environment. But for many utilities, the cost of energy during the monthly or yearly peak is hundreds or even thousands of times higher than the median price per kilowatt hour. This can provide a huge incentive to invest in DERs and energy storage solutions in particular. In addition to providing immediate power supply cost savings, peak reduction can avoid or reduce the size of costly infrastructure upgrades on the scale of billions of dollars for U.S. utilities over the next decade. Camus has found our co-op utility partners are exceptionally interested in this mechanism to reduce their members' rates. Public utility commissions are starting to come around to incentivizing investor-owned utilities to reduce consumer rates as well via peak demand programs. With the growing backlog of DER interconnection requests and the rising cost and lead time for distribution transformers, flexible interconnection provides a path to maximize the value of existing grid assets for utilities and their customers, whether through direct control by the distribution system operator or through emerging third-party aggregators. Letting DER resources operate up to a flexible operating envelope can accelerate interconnection and reduce T&D upgrade costs. These operating envelopes rely on forecast values for individual meters and DER systems. While SCADA meters can provide near real-time visibility at feeders, enabling flexible interconnection relies on knowing the current and near future load at meter level. We use these weather-driven nowcast forecast meter values to run feeder-level power flow models. With the power flow results, we construct operating envelopes that curtail DER resources to avoid safety limits or prevent voltage violations on the grid. In the near future, we plan to use actively controlled DER to support grid loads that wouldn't be possible otherwise without system upgrades like reconductoring or transformer upgrades. Thank you for joining me on this journey. If nothing else, I hope it's clear that I'm excited about this work, and I hope the ESIG community will be too. If you see value in what we shared here today, please support NOAA, including NODD, NCEP, and IUs. Please talk to your federal delegates and let them know how important this data is to the energy industry. For utilities and energy system organizations that want to use weather data, there are lots of options to partner with existing experts to get off-the-shelf solutions for complete grid orchestration solutions, to weather data providers, to expert consultants and open source developers for hire. There are many possible avenues. For organizations that want to develop in-house capacity and contribute to the accessibility of weather data, you can either engage with the existing communities to support your needs or engage your software engineering resources to build on these tools. Thank you so much for your time today, and I look forward to answering your questions.
Okay, thank you, David, and thank you, Adrienne. I've been just scrolling through the questions here in Slido, and Patrick, it looks like you've been busy trying to answer the questions as they've come in, but the questions have been voted up and down, and I think it would be illustrative or useful to go through the questions one at a time, and maybe David will have some insights to add to them as well. So let's just take a look at the questions that have been posted here. And Adrienne, the first one is for you. Can you please describe the kind of applications that use these data? I saw one of Patrick's responses that said he wasn't aware of all of the applications used, but maybe you or David could describe some of the ones you're aware of.
The list is so long, it wouldn't actually provide any real insight. I'll essentially say what Patrick said, which is that it's used by a wide variety of applications, and many of them we're unaware of until folks reach out to us. So one of the cool things about having the data on the cloud and periods of record and that kind of thing is that data is often utilized for things other than what it was intended. An example of this is NexRad data, which we all know, right, is meant to look at clouds and understand weather. But when there are no clouds, you can use NexRad to look at things like bird populations, which has been done. And there's an article that came out in the Washington Post some years ago about a bird study that had been done where we had lost 3 billion birds over something like 30 years. And they knew that because they'd been looking at NexRad data. So there's a lot of different applications. Go out and find one.
Are there any, I'm sorry, go ahead.
No, I was going to see if Patrick had anything to add to it, but honestly, we hear from a huge range of all different types of folks. As I said in the presentation, both inexperienced and very experienced at all different kinds of sectors.
I was just wondering if there was any categorization on your website, maybe groupings in different industries that show where the data is being used, but you don't have.
We don't have that currently
Okay.
because again, we don't know who the users are until they tell us. So we do in office hours, like we figure out like whether it's industry or academia talking to us, but other than that, we don't know.
Okay. David, do you have any visibility into this or any idea of any other power system applications or weather forecasting applications that are in use, or is your view pretty well restricted to what you're doing at Camus?
My views pretty heads down on the Camus application. I think ESIG's done a great job of covering the community of use in energy systems. I know from my previous work, with the NSF Ocean Observatories Initiative, how important this modeling data can be, and my work doing consulting with RPS. Certainly the oil industry is very interested in weather data and understanding ocean and weather data. I know there's a lot of use there. It's and I know the models in particular are used by the FAA. Among others, I know RPS supports using both ocean and weather data for the U.S. Coast Guard and the National Weather Service. For forecasting vessel icing was one of the really cool things I got to work on early in my career. When the fishing vessels come into New Bedford in the winter, they come across the Gulf Stream, and if there's a strong offshore wind, cold offshore wind, they build up sea spray icing on the upper decks and can quite suddenly flip over and kill everyone on board. And so forecasting those kind of conditions, they're just all kinds of applications, as Adrienne was saying.
Okay, thanks for that. FERC Order 881 requires live air temperatures around a power region, or I would say maybe a service territory. Can NODD be used to get current temperatures from given stations without a third-party service?
I feel like the answer to that is yes. Patrick, are you available? Do you think my problem is that I don't know which data set would provide you with the particular station. But if you go to the website and you check and you look at the data available and go to the landing page of each of the CSP and look at the metadata provided for you on the data set, you'll be able to figure out some of this.
Okay.
Yeah, that is correct, Adrienne. I think it just depends on where the data is, or that you're asking about. Where does it reside? What type of actual data set? If those are live weather stations, then potentially we also had conversations with Weather Service about getting ASOS 1-minute data onto the program, which I believe would provide information in and around airports. But I think we would have to know, again, exactly kind of what given station you're speaking of and who the owner and operator of that is, and then we could get a better response there.
Okay. I would as a follow-up question to that. It seems like you have just a massive amount of data available, an incredible mind-boggling amount of data available. And for people who aren't quite so familiar with all of that data and how it's organized and what the different weather service applications or sources are, is there any commercial firm or any other firm besides your office hours that could help somebody navigate his way through the database, and ask a question like this one and get some guidance as to how to follow up or where to go to get what he's looking for? Or is that pretty much up to the individual user?
I don't know currently of an enterprise that does that. It's a great idea. I think if our website is actually pretty helpful because it breaks the data down into the line offices. The NOAA line offices are basically broken down by the types of work they do, right? So there's weather is in the Weather Service. The satellites are in NESDIS, for example, ocean data and NOS, et cetera. They're split out that way. So the data sets are literally listed under each of the line offices. So you can see the data that's available. Now, I do want to highlight that NODD does not have all of NOAA data. But you can see what's available on NODD. You can ask for other data as well. And again, if you're looking at the metadata on the landing pages, that will tell you a lot about the data. You could also, Patrick, aren't there links to the actual data programs themselves on the?
Correct. The data sets actually link back to the actual program that produces that data set. So then you could learn more about that. And then also usually have access to communication strings to get back to those data owners, whether instead of just reaching out to us, those sites may also have contact information for the data owners.
That's a good point. Thank you, Patrick. But you can always ask us and we will get your question to the right place if you do not.
Okay, thanks for your clarification. Hi, David. What do you think of NVIDIA's ForecastNet? It claims to accurately forecast weather comparable to numerical PDE-based methods.
Yes, there's a lot of talk and excitement around using neural nets in forecasting. The NVIDIA solution, there's Google's GraphCast, among others. I think Dave Turner's comment at the end of his presentation on similar question was fantastic. That those models show a lot of promise and are going to be very important in the future. At the moment, I think they lack the ability to get the sort of coherent variables, the temperature and pressure at the same place at the same time, lined up in a way that's physically consistent and can be really important for either energy industry or just alerting about thunderstorms or public hazards, tornadoes, things like that. Where they're really good at getting reducing the root mean squared error around any particular variable. The coherence of it is difficult, and I haven't yet seen one that is publicly available producing downward short radiation and the meteorological information you need for PV forecasting. let alone the turbulent boundary layer structure that you'd need for wind generation. So there's a lot of promise there, but not quite there yet. And I just note that I think at least so far, most of those models are initialized and forecast from that assimilation product produced by the NCEP team at NOAA. I think some of them now use both the initialized state of the model from data assimilation and some of the direct field observations, but they're trained on and intimately related with these physics-based models. But the combination of the two is almost certainly the future.
Okay, thank you for that insight. I guess it looks like another question for you. How does Camus manage to produce sub-hourly forecasts by using the HER, given its hourly resolution? What other data sources does Camus leverage to do this?
So we can do interpolation from the hourly HRR data when we have 15-minute level meter data or sub-hourly meter data. We can also use the sub-hourly products from the HER model. There is a sub H product that is 15-minutely, and we're starting to explore using that more for the first 18 hours, the sort of nowcasting for first 18-hour forecast. But after that, you drop to hourly, up to 48 hours, and then with GFS, you quickly drop to every 3 hours. And trying to make the best of the data you have available is the art of the thing.
Okay. A question from Doi. Are there any applications of using weather data to price financial contracts for electricity in wholesale markets?
I think the answer to this is yes. I'm pretty sure. Jenny, are you available to respond?
Hi there, this is Jenny. You want me to do it verbally here?
Yes, please.
So we do financial contracts for electricity in the wholesale markets are complicated, and they're based and designed by different locations and by different setups. I think in this case, the question I almost have to ask for specificity. Wholesale markets rely on reliability of forecasts, and they come from solutions like Camus and the reference that Adrienne provided of Circle Solutions is now acquired by Enverus. So it's a little bit of, how can the analytics help inform the predictability of solar and wind and other availability of energy generation capacity. And it also depends on what's happening with the weather at the time and the capacity of that particular utility and what their needs are. So short answer is, do we have any examples of weather data used to price financial contracts indirectly? We have not developed or pursued any case studies directly. We like to work with finding the solution providers like Camus and others who figured out the use of the NOAA data in the ability to generate reliable forecasts. Is that fair?
Yeah,
We're not in the business of electricity wholesale markets. I just happen to live in that industry prior to this job.
Okay. David, any further comments on that?
Yeah, I mentioned a couple different partners and other companies I've come across in my recent work, but there's a whole world of folks that are focused at the ISO level and the wholesale day ahead market world. Some of them do run their own weather forecasts as well, downscaling to a particular region to refine the boundary layer for wind generation or refine the PV forecast. But all of that is connected up to the NOAA models so that you to get the initial conditions and the boundary conditions for the work that they're doing. So it's just a matter of how indirect, but all that data flows through NOAA and almost certainly is being accessed via NODD.
The clear answer to the question is yes. And for those of you who are at the forecasting and markets workshop that we held in Salt Lake City, I guess it was just last week, this question was front and center across the entire workshop, and tremendous applications for it in the ISO markets for sure. Okay, cloud providers are storing the data for free and providing access for free. What's in it for them? Is it people using compute services to process the data?
Well, that's it exactly. It's a great question. You'll recall I talked about the fact that especially if there's a lot of data, right? If they're using really big or they're doing very large analyses, they're staying on the platform to do it. So NOAA data is driving users to the platforms, and then you pick the platform that you like. So yes, that's why the cloud service providers everyone needs NOAA data. So everyone will check out NOAA data.
Okay. Are there plans to provide data in cloud optimized formats such as ZAR and COG?
We're just starting to get into that, but I'll let Patrick speak to that a little bit more. Patrick?
Yeah, great. Thanks, Adrienne. Yeah, so we are starting to get into a little of that. We do have some operational forecast system products that are being put up, and that page actually just went live earlier this morning. I think I included a link somewhere there. If you kind of scroll down towards the bottom of the questions, that is the registry.opendata.aws/NOAA-NOD-Kerchunk. There's some operational forecast system data sets that have been optimized there. There's also things like the national blend of models that are produced in COG right now as well by the data owner within the Weather Service, and some other data sets that are being looked at. I will say, though, that NOD itself does not really do any kind of data conversions and everything, but this is a larger conversation that is happening within NOAA to encourage data owners within the organization to look at cloud optimized formatting.
And if I could, I'd just reiterate that, any of these legacy formats that support the byte range access for the data you want really already are cloud optimized to some degree. There's room for improvement, and you could do more if you had multiple different sort of arrangements of the bytes for different access patterns. But we're already 90% of the way there with GRIB and NetCDF up on cloud storage. So the Kerchunk and virtually ZAR solution really just unlocked a whole new world for using this data.
Okay. David, another question for you. Can you please comment on use of this data for forecasting for large utility scale PV plants?
Absolutely. So far we've been working with the HRR forecasts, the downward short-wave radiation and so forth, to forecast large utility scale solar for our customers. We've been using the PySam library with custom built models for each solar plant based on the arrays and inverters that they have, and have shown pretty high fidelity forecasts that have been really incredibly useful to our customers. And that's only using them in a direct physical forecast mode. We're really looking forward to refining that where we have the need for the accuracy to combine that with a machine learning approach that would use the machine learning model to refine the physics-based forecast and correct the biases that might exist, or improve the direct physics-based forecast from the weather data through the PySam model. And there's a lot of room to go there. There are a lot of people that work on improving PV and wind forecasting in that way, and we have a lot to learn there. But the basic plumbing and the basic capacity to do it is something that we've definitely been doing operationally for our customers.
I think we've got time for one more question. This one is for Adrienne. You may have already provided the link, Adrienne, but the question is, could you please provide the link of your open source for wind and solar data? How is the resolution of the data? Thanks.
Well, because there are multiple options. So I'm going to direct you back to the website, and to review the metadata for the various options available because there are so many. And then if you have additional questions, once you start looking at that, feel free to email us at noaa.gov/nod. Sorry,
Okay.
not at noaa.gov. I gave you, yeah.
Yes, I think we've got the link in the presentation, if I recall correctly. Yeah.
Great.
Okay, so we're about at the top of the hour, so we're going to need to wrap it up. And I want to thank Adrienne and David for this very useful presentation. And I hope you all have a better appreciation for what's available from NOAA and how it can be used. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to. I see there was a few more of those down mixed in with Patrick's replies, and we'll get them posted as quickly as possible. We appreciate your engagement. I look forward to seeing you again soon. Stay tuned for the announcement of our next webinar in July and for our fall technical workshop in Providence, Rhode Island. Further information on all of our webinars and meetings can be found on our website at esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. Adrienne and David, thank you once again for this really informative webinar, and thanks to all of you for your engagement. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks for your participation.
Thank you, Charlie. Thank you, Adrienne.
Thank you, Charlie. Thank you, David.
Thanks, David. Thank you all.